So we've seen basically what this latch is. Right, in a very simplistic sense, this is what is going on. Alright. So one thing I need to add. Alright, so I'll now talk about another practical issue that's there in most analog systems, and today it turns out that most analog systems on a chip are what are called fully differential systems. Okay, so how many of you have heard of this term, fully differential? Okay, so let me explain what it is and why people do this. All of you realize that on a chip there is some analog and there is some digital stuff, right? And in the simplest case, all these guys are running off of the same supply, right? Now, what do you think if I kind of look at the power being drawn by, rather the current waveform being drawn by the digital part of the circuit? What do you think that current might look like? Huge spikes at what, I mean, every time, or are there some times when the spikes become particularly large? So if you use standard CMOS logic, there is in fact no current at all, or there's leakage current, which is a small DC component at all times, right? And during this clock transitions or switching transitions, there will be huge spikes of current. Okay. Now, if the voltage supplying the chip was an ideal battery, correct? Then what do you think would be happen to the voltage? What do you think will be the voltage waveform here? It will be VDD because the battery is an ideal voltage source. Okay. In practice, the battery is not ideal. Not only that, right? The wire that you use, the trace on the PC board that you use to connect the battery or the voltage source to your chip has a lot of inductance. Okay. So what is so special about an inductance? I mean, do you think now we are all okay, or there's a problem? This is the inductance. Pardon? Okay, the inductor opposes change in current, so what? So what happens now? Correct. So basically what happens is that the inductor is a short for DC, but will not, as you pointed out, allow sudden changes in current. Correct? But unfortunately the digital blocks draw a lot of current only during transitions. So the current waveform here is very spiky, right? There is huge spikes at every clock transition. So what do you think will happen to the voltage here? If there is no inductance, there is no problem. If there is inductance, what happens? supply bounce or ground bounce. So why is that happening? That's happening because the inductance cannot tolerate a sudden change in current. So if the current here changes suddenly, what happens? The inductive impedance becomes, the voltage across the inductor is L di by dt, correct? Di by dt is infinite or very high at any rate. So this voltage will attempt to fall down, right? Ideally it is VDD, but every time there is a clock transition it will attempt to fall. Unfortunately, the analog and digital portions of the chip are sitting on eventually on the same supply, correct? So what do you think happens to the analog? If you take an analog circuit and start varying its supply, what do you think will happen to the? Basically, whatever is there on the supply will also, for example, if you have a common source amplifier, correct? If this changes, the output voltage here is nothing but the quiescent voltage plus GM times the input plus whatever is there here. The gain from the supply to the output is 1, the incremental gain, right? If I yank the supply up by a small delta V, the output voltage also changes by the same amount. So you can see that supply noise gets in completely into the system, right? Because of this, and therefore if an analog, if the analog and digital portions of a chip share the same supply, all that you can do is you can, you can probably minimize the glitching on the supply, but you have to face the fact that the supply voltage will be noisy due to the junk that is going on in the digital port. Does that make sense? So what all can you think of to mitigate these problems? Pardon? Oh, well, 1 second. Before that, let's say you can't make any changes. What all can you do?
Separate and have star connection.
Separate and have star connection. More, at a more fundamental level. One thing you can try is to say, you should do, is to say that, okay, the inductor is not able to supply rapid changes is not able to accommodate rapid changes in current. So what you should do is put a capacitor there. It's also called a bypass capacitor or a decoupling capacitor. And what is the job of that capacitor? All the high frequency current comes from the capacitor. Correct? Okay. Everybody is familiar with this? Decoupling or bypass capacitors? Okay. But whatever you do, finally there will be some jump on the supply. You can only reduce it. You cannot eliminate it. So, obviously in very sensitive circuits, a small amount of supply noise can therefore completely kill you, because noise on the supply will just simply get into the IC. Okay? Alright. So, so in other words, we have taking the simplest example of a common source amplifier. Let me call this V noise, and this is some V bias. Let's say the GM of the transconductance of the transistor is Gn. This is R and the quiescent current is I. What is the quiescent voltage here? VDD minus IR is the quiescent voltage. What is the incremental voltage at that node? Minus GM times VI times R. Then what else? Plus VI. Correct? This is the quiescent. This is because of this character, and this is because of this guy. Correct? Okay? Is that clear? So, even in a simple common source amplifier, we see that the output of the amplifier can simply get corrupted due to supply noise. Okay. So, and as we just discussed, you can always minimize or reduce supply noise by decoupling and that kind of thing. But it is not possible to eliminate completely. So, any suggestions? What do you think I can do? Can we do something to fix this problem? Yeah. So, what you can do is to say, hey, what I'm going to do is copy and paste this circuit. Make a copy of this guy. Right? This, and I'm going to say I will operate this with a signal like this, and I'll operate this with VIM, which is minus VI. Right? In other words, something like this. That is this guy. So, this voltage, the incremental voltage here will simply be minus GM R VIP, correct? And this voltage incrementally will be minus GM R into VI M. And then what about the noise component here? Vn. What about here? Plus or minus? Plus Vn. Correct? So, the key point is to note that if I do not consider my signal to be either VIP or VIM, but the difference between the two, okay. So, in other words, what I am saying is that the input is VIP minus VIM. The signals individually are of no consequence as far as I am concerned. And the output is what now? If I am not interested in either the absolute voltage here or the absolute voltage here, but if I look at the difference, what is it? Minus GM R times VIP minus. Okay. In other words, what has happened? What do you see here? This Vn has gotten eliminated completely. Correct? So, in other words, Vn being a noise source common to both circuits has gotten rejected. Alright? So, even if the supply voltage varies a little bit, it does not matter. It affects both legs. But when you look at the difference between the two legs, the variation in the supply has been eliminated because it is common to both legs. Correct? So this is what is called differential signal processing. Okay, where the signals of interest are not the absolute quantities, but the difference between two lengths. Does that make sense? Okay. All right. So, in other words, when we were talking about flash converters, we were saying we will compare Vn with whatever, V1 and so on, right? So now, if you go into fully differential circuits, what do you think we should do? This input difference is not any single voltage, it is the difference between one going up and one going down. So this is represented as VCN plus VI and VCM minus VI. So whenever you have two voltages, you can always express them as their average plus an increment and their average minus the same increment. Correct? So if you have two voltages, you can always express them as the average, which is often called the common mode. Correct? And so one of the voltages will be common mode plus differential mode. The other one will be common mode minus differential mode. Correct? And now you have to compare this signal where the information is basically in the difference between the two voltages, and what would you do with the, as far as the reference is concerned? You can always also make the reference also differential, correct? So VCM plus Vref, not Vref, I mean plus V1 and VCM okay. The input corresponding to these two, the quantity of interest is 2Vi, the quantity of interest here is 2V1. So comparing Vi with V1 is the same as comparing VCM plus Vi minus VCM minus Vi with VCM plus V1 minus VCM minus Vi. Okay. This way you are actually immune to all common mode or all disturbances which are common to both. I mean, clearly this would involve copy paste. Correct? You have two sets of circuit, I mean two sets of hardware, one which processes the input, okay, some voltage, and the other half which processes minus of the input. Correct? So when you look at not the individual outputs of each of these blocks, but the difference, any noise that is coming which is common to both halves will just get eliminated. Okay? And this is now a very routine and standard technique in all analog processing. Otherwise you wouldn't be able to build most circuits that we're able to today, simply because the common mode noise can be so much so that can really kill you. Alright? Okay. So now we spent a lot of time figuring out how to compare Vn with V1, all the latch and stuff like that, right? Now what we are interested in doing is figuring out, all that stuff is okay, but what we are interested in actually doing is to figure out the differential difference. What we want to do is VCM plus Vi minus VCM minus Vi, this minus VCM plus V1 minus VCM minus. Is that clear? Because this is now the input that we are interested in, this is the reference that we are interested in. Okay. For example, if we wanted to compare if the differential voltage is greater than 0 or less than 0, then what we would do is basically V1 would be 0. That's all. If you wanted to compare with the threshold of 0, this is what we'd like to do. Okay. So this is actually fairly easily done. So in other words, we take a standard latch, so what will happen now? If Vi is greater than 0, what happens? We call this node A and this node B. So VA will become greater than VB. Eventually, after the regeneration phase, what will happen? V will become VDD and VB will become, here please note that we got rid of the minus VDD. The minus VDD we had earlier is now nothing but ground, right? So VA will go to VDD, VB will become ground. Okay. Now we need to be able to, so A or B go to okay. Right? Okay. So, but what we want to do is compare VCM plus VI minus VCM minus VI with VCM plus V1 minus VCM minus V1. So any ideas on how we might be able to do this? What all do you think we can do? No? Okay, go ahead. One more similar block. Yes. 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 Oh, see, one problem, okay, so what, please notice one thing, what we are getting is basically out of this block, A and B, they will regenerate and tell you whether the difference between these two inputs is greater than 0 or less than 0. So what you can't do the following, which is, I will use this copy paste, use VCM plus V1, VCM minus V1, and I'll get two digital outputs, correct? Each one of them is telling you whether Vi is greater than 0 and if V1 is greater than 0. Do you understand? So, clearly what that indicates is that, see, this making a decision, regeneration, finally the output is non-linearly dependent on Vn. It's only telling you whether the input is greater than 0 or less than 0. So, but we want to subtract Vn minus V1. So, any subtraction has to be done before you try and make a decision. Is that clear? You can't use this comparator and then use comparator 1 for input, comparator 2 for reference and then subtract the two outputs. That doesn't work. That's clear? So whatever you have to do, the subtraction has to happen before the comparison happens. Does that make sense? Okay. So if you want to subtract two voltages, what do you think you can do? If I have two voltages V1 and V2 on two batteries, what do you think I can do? How will I get V1 minus V2? I have two batteries, one is a 9 volt battery, one is a 1.5 volt battery. I want to get 7.5 volts. What will I do? Adding voltages, if you have voltage sources, is easy. You just take the voltage sources and then connect them in the right polarity. Correct? So, let us assume that we have a battery of voltage V1 somehow. If you have a battery of voltage V1, one way of generating this is VCM plus Vi, this is V1, correct? And this is VCM minus Vi. And this is minus V1, so this is also V1. Correct? So what is this voltage? VCM plus Vi minus V1. This voltage is VCM minus Vi plus V1. Correct? So, now if we use this comparator, what happens? A will be equal to VDD if VCM plus Vi minus V1 is greater than VCM minus Vi plus V1. Correct? Does that make sense? So, which is equivalent to saying you understand? Okay? Alright? So what do you think I can do with, so how do I get a battery? Obviously, I can't run to the store and get a battery, right? Every time I need a threshold, I'll need thresholds of Vref by 2 to the n. So obviously putting batteries on the chip is not a practical idea. What do you think I can? Yes, sir. Summing amplifier. Okay. Any other idea? Series of? Let me see. Yes. So what